Hello, good morning, student. So, what did we discuss yesterday? We discussed about trans 1,2-dimethyl cyclohexane. So, today we are going to learn the remaining point of this chapter, that is a third type we are going to learn. And what is that third type? Is a 1,3-disubstituted 1,3 type, right? 1,3 type disubstituted cyclohexane, 1,3 type, that we are going to learn here. Now, does this type shows a geometrical isomerism? Yes, it shows a geometrical isomerism. Geometrical isomerism like as a cis and trans. And similar to the 1,2 type, the 1,2 type also showing two geometrical isomerism, cis and trans. Similarly, 1,3 type also exhibit the cis and trans isomer. Let us start. First one, A is called as cis isomer, which is known as, which form it is? AE form or EA form or AA form or EE form. What do you think? What is your opinion? So here must be AA or EE form, right? Here why I am talking about AA means axial, E means equatorial. Both the substituent present at this position, so we can call it as AA or we can call it as a EE form, right? AA form or EE form. And generally we are considering the general example is cis 1,3. Here is a cis isomer. I think some here cis. Here you write 1,3 AA or EE form, and here cis 1,3 dimethyl cyclohexane, right? Now, cis 1,3 dimethyl cyclohexane, and as we know that in case of previous example 1,2 type, there we have seen in case of the cis isomer and the trans isomer, total number of the structure we got as a 8. Now here also we are going to start with 1, 2, 3, 4, 5, 6 and 8. Same type we are going to learn here. Only the difference is that the methyl group were present at 1, 2 position. In this case, the methyl group present at 1, 3 position, and that's why it is a third type. Now let us see the structure of that. Let's draw the structure first. This is as we know that AA form means what? One of the methyl group which is present here, another methyl group 1, 2, 3, right? This you can number 1, 2, 3, 4, 5 and 6. 1, 2, 3 at 3 position, methyl group is on the axial position. Look at, if you put hand here, what do you see? The methyl group is present above the plane. Here also if you put as a finger, what do you see? Here methyl group are coming on the same side of the general plane, and this type of the conformer is known as cis isomer. This type of the structure is known as a cis isomer. Both the substituents are on the same side, and therefore we can call it as this is a structure number 1, right? And now structure number 1. Now let me show you the model, how it looks. By looking as a model, see this model, the black indicate as a number of carbon atom and white indicate as a hydrogen atoms. Look at here, this is a chair conformation of the cyclohexane. Assume that this is a methyl group which is above the plane, another methyl group which is also as above the plane. You can see the clear model here, and from that we can easily find out, by looking the model we can easily find out it is a cis conformation, right? This one, both the methyl group are on the same side, and therefore it is a cis isomer, right? And this one, and now this first one, and as we know that there is a one process, which is that process which is called as a flipping process. Flipping is a process where one of the chair conformation is converted into as another chair conformation, and during that process what is happening? Do you remember? The axial bond becomes as a equatorial, and equatorial bond becomes a axial one. This above carbon atom, it goes below the plane, and this fourth one goes above the plane, and therefore you can draw the structure is like this. This you are going to get as a structure here, right? Now this is a carbon number 1, carbon number 2, carbon number 3, 4, 5 and 6, right? We are following the same numbering system here, clockwise manner. Now look at here, one subtotal methyl group which is above the plane, it remains above the plane, but this axial is going to become as a equatorial one, and as we know that this is a equatorial position, right? This is above the plane, but it becomes as a equatorial one. That axial becomes as a equatorial, that during the flipping process. Now look at 1, 2, 3, at 3 position, that methyl group where it that is axial position, where it goes at a equatorial position, and equatorial position is like this, methyl group at equatorial position, and therefore this we can call it as a structure number 2, right? Now what is the next? As usual we know that we drawing here is a dotted line. What is that dotted line represent? This is nothing but as a mirror, right? Okay, this is a mirror, and that mirror, what is the purpose of mirrors? You can see your image in the mirror, or you can see the mirror image of the object, any object. This is one of the object, or this is a structure, you can see its mirror image into as a mirror. How does it looks? It looks like this. Let us see here. It looks like this. This is a structure, right? Now this axial group which is present at axial, then this one, this carbon number 1, 2, 3, 4, 5 and 6 as usual at 3 position, which is also above the plane, right? And now what is the next step? Next step is as usual, it is a flipping process. After the flipping, and this structure you can call it as a structure number 3, right? And now after the flipping, what is going to happen? This above that goes below the plane, and you are going to get the structure like this, right? Now this is a carbon number 1, 2, 3, 4, 5 and 6. At carbon number 1, which is axial one, after the flipping, it is going to convert into as a equatorial one. At carbon number 3, 1, 2, 3, which is going to become as a equatorial one, it looks. If this is a structure number 4, observe this structure carefully, and what do you see? This is the mirror image. If you flip it, you are getting this. If you look here, this is the mirror image, exactly mirror image of each other, right? And therefore this is the what we can call it as a way drawn the structure. 5 mark questions always there. What type of the question? Yesterday I already altered that question. Now I am repeating it. Draw the chair conformation of cis-1,3-dimethyl cyclohexane. What is that? Draw the chair conformation of cis-1,3-dimethyl cyclohexane, full stop, and explain or comment on its optical activity and the stability. So that is a 5. And if you draw this structure, 4 structure correctly, you will get as a 3 mark. And to state the whether this compound is optically active or optically inactive, then you will get 1 mark. And finally you determine the energy associated or consist in the conformation, that will give you the 1 mark. So in this way the distribution of that 4 mark, while we are normally teacher is there is a model answer, scheme of model answer, so we are giving. So if the student are drawn as a 3 structure correct structure chair conformation of cis, then you give the 3 mark. Then suppose as a optical activity, if it's a correct mentioning, give 1 mark. And then for stability 1, if correct determining 1 mark. So this way you can maximum mark are getting in the organic chemistry. And remember, organic chemistry just like as a mathematical, you will get out of mark or maximum mark. Similarly there is a possibility also there, minimum mark also you are getting here. The some of the student facing very difficult in organic chemistry to understand, those are listening the lecture carefully, they can understood the basic concept of the organic chemistry, and they find organic chemistry is a very easy subject than the other subject, because here just as a you have to concentrate what the teachers are explaining, and if you understood once, it's very easy, no need to study again and again. Once you know the basic concept, you can very easily understand. Okay, these are the 4 structure correct, 3 mark. Now what is the next point we are going to discuss? Second one is the optical activity, right? Second one is a optical isomers. Optical isomers means what? You have to find out whether this compound is optically active or optically inactive. And for determining or for recognizing or for finding the optical isomer, what I already explained this concept again and again. What is that? You have to find out, you have to look the model, you have to observe this structure carefully and find out, is there any mirror plane of symmetry is present. If it is present, that compound is optically inactive in nature. If this structure has no element of symmetry, that structure or that isomers are optically active. Remember, optically active. If plane of symmetry is present, molecule is optically inactive. No plane of symmetry, molecule is optically active in nature. Now what do you see here? If you see this compound, what do you think about here? Your opinion whether this cis-1,3-dimethyl cyclohexane, whether it is optically active or optically inactive. For that purpose you observe this structure carefully. If you see this structure, or students are advised to see the model carefully. If you cut this molecule from this, you will get the identical 2 parts of that molecule, and therefore if it is there is a plane of symmetry is present, and therefore these compounds are optically inactive in nature. Optically inactive because there is a plane of symmetry. There is plane of symmetry is present. Plane of symmetry is present, and plane of symmetry is present, and due to that reason this molecule becomes as a meso compound, and meso compound are optically inactive in nature. At the beginning in a cis-1,2 dimethylhexane there is no plane of symmetry present, but that molecule are the racemic mixture, and that's why cis-1,2 dimethylcyclohexane is found to be optically inactive. Similarly, but here there is a plane of symmetry, and therefore this compound is optically inactive in nature, and because there is a plane of symmetry is present, and this compound becomes as a meso. Now look at the model again very carefully, and if you look at this model, if you cut this model from the assume that this carbon number 1, 2, 3, 4, 5 and 6 are there. If you cut from this, you will get the two exactly identical compound, and therefore that is there is a plane of symmetry is present, and therefore this cis-1,2 dimethylcyclohexane is optically inactive in nature. One more question also may appear in your question number 4. Cis-1,3 dimethylcyclohexane is optically inactive. Why? Question mark. And at that moment, while answering that question, you just draw any one of them structure 1, 2. Either you can draw this structure, this structure, this structure, or this. Only one structure is sufficient. You draw one and then mention there is no plane of symmetry, and therefore that is optically inactive in nature. Because that question already included the answer, you need to state the reason there. That's it. Okay, this is all about the optical activity. Now third point. What is the third point? Generally we are talking about that is a third point. We are talking about the conformational isomerism, right? Conformational isomers or conformational isomerism. Now look at, there are the 4 structures are there. The structure number 1st and 3rd, what do you see? They are the, suppose 1 and 2nd, they are the enantiomer. Similarly 2 and 4 are the enantiomers. And whereas what is the relationship between 1 and 2? 1 and 2, they are the diastereomers. Similarly 3 and 4 are the diastereomers. So this type of the, and enantiomer, you know that they are the non-superimposable mirror images of each other, are known as enantiomers. But here this compound is a meso compound, and that's why it is optically inactive in nature. Diastereomer means they are the totally different in the reactivities. If you next point we are going to talk about the relative stability of this conformation. Now when we are talking about the relative stability, 4th point, let us cover here itself in the relative stability of these conformers. Now let us look at as a 4th point is a relative stability. 4th point is a relative stability. Relative stability, right? In the relative stability, what do you see? There is you have to find out 1,3 diaxial interaction and N-butane Gauch interaction. What do you see here? Look at here. 1, 2, 3. There is a methyl group. 1, 2, 3. There is one of the hydrogen atom here. One of the hydrogen atom at 1, 3 position. What do you see? There are 2 CH-3H interaction. So 0.9 into 2 becomes as a 1.8. kilocalorie per mole. This much amount of the energy associated with. Now one of the methyl group, they are 1 2 3, they are 1 3 position, and when they are 1 3 position, they are goes to each other and they are creating or they are producing 4 times greater energy than the 1,3 diaxial CH3H interaction, means 4 times. So you have to take 0.9 into 4 times, because this methyl group, they are present at 1 3 position, so 4 times they are generating of the van der Waals strain are there, and therefore 0.9 into 4 is equal to 3.6. If you add this, total becomes as a 5.4 kilocalorie per mole. This much amount of the energy associated with these molecules. Here 5.4, this is the same, therefore 5.4 kilocalorie. Here look at in the structure number second and the fourth they are the same, but equatorial position there is no 1,3 diaxial interaction, similar as well as there is no n-butane gauge interaction, and hence this is heat has a 0 kilocalorie per mole. This is also has a 0 kilocalorie per mole. If you compare between these two, it is a least stable and this is a most stable. Remember, di-equatorial conformation is more stable than the diaxial conformations are there. So I think with this, let us stop today here. Remaining we will see the next time, which is trans isomer. So thank you. Have a nice day.